Earth's atmosphere is extremely thin compared to the size of the planet. If Earth were the size of a soccer ball, the atmosphere that we live in would be as thin as a single layer of plastic wrap. When you fly cross-country in a jet airplane 6 miles above the ground, most of the atmosphere that creates weather is beneath you. It rapidly thins with height. Weather occurs in the lowest layer of the atmosphere called the troposphere. It's where there is rising and sinking motion due to uneven heating from the sun and from varying topography. The air in the troposphere is mostly nitrogen and oxygen, with small amounts of argon, carbon dioxide, hydrogen, and other gases. Air also holds varying amounts of water vapor. That is vital to life and weather. In the troposphere, the temperature gets colder with height. The amount of water vapor decreases with height, and the air pressure decreases with height. There's less air as you climb in altitude, so it is less dense and cannot hold heat very well. That is why the tops of tall mountains, even near the equator, remain cold with snow on them. The one thing that does increase with height is the average wind. These winds above the ground are what steer weather systems around the Earth. Given the greater density of the gases and water vapor low in the troposphere, a large amount of the sun's heat is trapped near the ground. Without the troposphere, planet Earth would be a much colder place, unsuitable for life as we know it. Sometimes temperature does increase with height. This is known as an inversion because the temperature trend is inverted from typical. Temperature inversions result in stable weather because the warmer air aloft limits rising motion or convection. They are not unusual after clear, calm nights with no wind. When temperature inversions persist for days, they can cause bad episodes of stagnant air and pollution. The atmosphere as a whole captures and sends back out to space about 30% of the radiation arriving from the sun. For the other 70% of the radiation, most reaches the ground, where it is absorbed as heat, while a smaller portion is absorbed directly by air. That's not the end of the process. All incoming solar radiation, also known as insolation, is re-emitted at different wavelengths between air and ground and clouds and water. Ultimately, there is a balance between the amount of energy coming into the Earth's atmosphere and the amount leaving. This holds the planet at a nearly steady temperature. Most of this balance occurs in the troposphere. The three components of the balance of energy are radiation from the sun, conduction of heat absorbed at the ground to the air adjacent to the ground, and convection, or rising air currents in the atmosphere. Beyond the troposphere is a layer of the atmosphere where there is not much rising and sinking motion. The air movement is mostly horizontal and stratified. This layer is called the stratosphere. There's very little oxygen there, but there is ozone, which absorbs radiation to make the temperature increase with height. The layer of ozone in the stratosphere protects life below from high levels of ultraviolet radiation. Ozone is a form of oxygen composed of 3 oxygen molecules, but we cannot breathe it. The oxygen we breathe is composed of 2 oxygen molecules. The tallest thunderstorms can reach the stratosphere, but when they encounter the stable air and horizontal wind of the stratosphere, about 12 miles up, they spread out and form a shape like an anvil. Because of the lack of moisture and air in the stratosphere, very little weather occurs there. 2 other layers exist beyond the stratosphere, the mesosphere and the thermosphere. These layers also protect us from high-energy radiation from the sun. The thermosphere is the edge of space. It is within the thermosphere where bursts of radiation interact with Earth's magnetic field to produce the aurora. High-energy particles travel from the sun in what's known as the solar wind. The particles constantly bombard our planet, and they are focused by the magnetic field around the North and South poles. These are not directly dangerous to people on the ground, but when the sun emits large quantities of them, they can disrupt GPS systems and interfere with electrical power grids. They may force pilots to divert flights from over the poles for safety from excessive radiation in the upper troposphere. Most noticeably, this rush of particles across Earth's magnetic field creates brilliant displays of the aurora. Seen from the International Space Station, you can compare the aurora to the relatively thin atmosphere surrounding the Earth. Much of the aurora happens about 50 miles above the ground. A display of an aurora is a geomagnetic storm, and in the Northern Hemisphere, it's called the aurora borealis, or the Northern Lights.